Dear viewers, welcome to the YouTube channel H2O Chemistry. Our channel objective is the learning is stress free, as well as the learning should be a conceptual one. So when you learn with the proper examples, the student never forget those concepts. So that's what we are trying to do in our channel. So let us start with a topic called periodic trends in the properties. See, in the initial class we have said that what is meant by periodic. The periodic means anything which repeats after regular interval. So that is an idea, my dear children. Anything which repeats after regular interval. A particular interval, some property will be repeated or something will be repeated. Such a case we call periodic. What about trends? Trends means a pattern. So this idea is very useful. Trends means pattern along the period and across the group in the periodic table. So this is an idea, my dear children, to understand this concept. Understand? So the pattern along the period and the group we are going to discuss in this. Okay, before that, let us see what is the meaning of this periodic. So in order to take this, let me write some elements: lithium, beryllium, then boron, carbon, nitrogen, oxygen, fluorine, neon, right? So the next element is sodium. So the next element is potassium, like that it goes. And then the atomic number of lithium is 3, the neon is 10, the sodium is 11, the potassium is 19. So it goes like this. So in this, I want to check this periodicity. What is meant by periodicity? See, let us quickly write the electronic configuration. Lithium 2, 1, sodium 2, 8, 1, the potassium 2, 8, 8, 1. So in their last shell, they have one electron, right? So when they form an cation, lithium will form lithium 1 plus electron. So what is the valency is 1, right? So when they react chemically, all the group 1 elements behave similarly. So that is an idea, my dear children, right? So the periodicity repeats after every particular interval. Check out. So from lithium 1, 2, 3, 4, 5, 6, 7, 8, 9. So the 1 and 9th elements have a same property in the second and third group, right? So that is an idea. So there is an particular property is repeated at regular intervals, right? So we are going to check such a properties along the periods as well as group. So that's what we are going to do in the periodic trends. Got it? Now this behavior is called as periodicity. So what is called periodic we have seen. So this behavior is called periodicity. Now let us go to the next one, that is what are the properties we are going to discuss in this. The properties of an element we are going to discuss is the first one, atomic radius. The next one, ionic radius. The next one, ionization energy. The next one, electron affinity. The next one, electronegativity. So these are the properties we are going to discuss in this periodic trends in the properties. So let us discuss one by one. Let us go to the first topic, that is atomic radius. Now, so we can say a size of an atom we have to be considered for this. So very important, my dear children. Okay, let us draw a circle first. A circle I have drawn. So from the center, if you measure to the outer line, it is called radius. It is called radius. So let us look at for the atom. For example, first group. Got it? First group, let us look at the atom. So let us go to the lithium. The atomic number is 2. In the K shell we have a 2 electron, L shell we have 1 electron. So the helium has a 3 protons, that means 3 plus in the nucleus. In the K shell it has a 2 electrons, and the L shell it has a 1 electron. So this is the structure. Am I right? Next come to sodium. So it has a 11 protons. K shell we have 2 electrons. L shell we have 8 electrons, right? Because K, L, M 2, 8, 1, that is the configuration. So 1, 2, 3, 4, 5, 6, 7 and 8. In the last shell, M shell, it consists of 1 electron. Am I right? So you could see now the atom is spherical in shape. When you see the cross section, you could see like this, right? Now how do you find the radius? So very simple. From the center of an atom and the distance between the center of an atom and the last electron, the valence shell in which the last electron present, if you calculate this distance, it is called R. So obviously it says lithium has a less radius than the sodium, because the outermost shell present in the L shell, whereas for the sodium is in M shell. So when the shell increases, size also increases. Now, so this is idea, my dear children. So can I make a definition out of this? Yes. So can I say like this? The atomic radius, it is defined as the distance between the center of the nucleus and the outermost shell, which consists of valence shell electrons. So this is the idea, my dear children. Got it? So now I want to just know that is it possible to calculate radius? Calculation of isolated atom, that means single atom, is impossible or not possible. So it is not possible because most of the atoms are not as single atoms. Remember, they do not exist independently except noble gases. So noble gases we have a single atom radius, whereas for the other atoms, most of the other atoms, we do not have this isolated atom radius. Instead, we have a two kind of atomic radius. Atomic radius we are calculating in two different manner. One we call covalent radius, another one we call metallic radius. The metallic radius is meant for metals, whereas for covalent radius is meant for non-metals. That is the idea, my dear children. Understand? Got it. So it's a distance between the center of the nucleus and the electron present in the last shell. So that is called atomic radius. That is called the atomic radius. So let us see one by one what is the covalent radius and what is the metallic radius. Okay, first we will go to the metallic radius. So we will see the first one, that is metallic, and then we will move on to the next one, metallic radius. See, we know that when you take a copper wire, The copper atoms are connected continuously like this, right? It's just a uh, continuously they are located like this. We call it as an metallic crystal, right? So if I know the nucleus, so this is nucleus, please imagine, right? So if I measure this distance between these two adjacent atoms, right? This is an atom number 1, atom number 2. So if I measure the two nucleus distance, internuclear distance, because the word inter means between two, internuclear means between two nucleus, internuclear distance means distance between the two nucleus. If I measure that, the atomic radius will be, so it's like a, right, diameter, right? So because distance between two, I want only half. So what I can do, atomic radius we can measure by internuclear distance of two adjacent atoms divided by 2 will give me the atomic radius. So this type of atomic radius is called metallic radius, right? So let us write the definition for this metallic radius. So metallic radius is nothing but the half of the internuclear distance of adjacent, right, adjacent atoms present in the metallic crystal. Metallic crystal is called metallic radius. It's called metallic radius because all the atoms are interconnected in metals. So when you measure the internuclear distance and make it half, we will get the atomic radius. So that is the answer, my dear children. So it's a half of a distance between the nucleus of adjacent metals. So in other words, we can write it is the half of the distance between the nuclei of adjacent metal atoms. So this is what we have to understood, my dear children. I hope you know this metallic radius is helpful. So this idea is helpful. Now let us go to the next one, that is covalent radius. So this is only for metals. So this only for metals. Remember this. So let us go to the covalent radius. We know that when non-metals bond each other, so let us take a case of hydrogen. So we have learned that hydrogen, the nucleus we have a 1 plus, in the K shell we have 1 electron, and when they bind with one more hydrogen, when it forms, so when the formation of H2, the electrons combine, sharing takes place. So in the hydrogen nucleus there is a one more electron will be there. So now both the electrons, right, comes closer and they are very near to this. Am I right? So there will be no electrons in that case. So now there is only electron. These two electrons are shared by these two atoms. Now let us calculate the distance. Similarly, the center of the nucleus and center of nucleus, if you measure the distance and make it half, you will get the atomic radius. Am I right? So this is also the internuclear distance, half of the internuclear distance in the covalent bonding. So this is an idea we have to learn, my dear children. So it's again internuclear distance. So let us write What is the definition of this? So when the formation of a hydrogen or a chlorine, this is what the happens. So chlorine, fluorine, so all are noble gases, even with oxygen. But we normally take a single bond. So between a single bond, what is the distance between an atom? That is we considered as covalent radius. Covalent radius. Understand? Now let us go to the covalent radius definition. The half the distance between the nuclei of two covalently bonded non-metallic atoms, right? Bonded atoms of a same element, right? So let us go and verify this. Yeah, if I draw hydrogen, the one more element will also be a hydrogen. So like this, hydrogen, hydrogen, there is a two electrons. Similarly, chlorine, chlorine, two electrons. So other shells are here, imagine. So the other shells will be like this. So there is a single bond between. So this distance, center and center, this distance, if you calculate and divide it into half, we can say it is a radius we call covalent radius. This is only applicable for non-metals, non-metals only. So we cannot compare the metallic radius with the non-metallic radius, because both will have a different value. So the atomic radius, I can say, we cannot compare the metal and non-metals. So it's a distinct property. Metal we can compare with the metal, but as non-metal we got to compare with the non-metals. So let us see some examples in this, my dear children. That is from the X-ray diffraction studies. From X-ray diffraction studies, the internuclear distance, what is this? They said is the distance between two hydrogen nuclei. Yes, so let me draw a diagram for that, right? H. So this internuclear distance, what they're given is 0.74 Armstrong. So can you calculate the atomic radius? Yes, atomic radius is nothing but internuclear distance divided by 2. So 0.74 Armstrong divided by 2. So if you cut it, we will get 0.3 times and 7. So the answer is 0.37 Armstrong. So this is an atomic radius of hydrogen. Understand? So now let us see some basic concept of trends. That means we call trends, how it vary, the atomic radius, how it varies along the period and group. Got it? So let us see the period first. Got it? Period first. Lithium, and then sodium, and then potassium. So this is, we can say, group, right? They are in the group number 1. So let us take the first 3 elements, we will understand. So lithium, KLM, so 2 comma 1, for sodium 2 comma 8 comma 1, for potassium 2 comma 8 comma 1. So if you draw a diagram, right, the lithium has short distance, sodium has got long distance, potassium has got very long distance. Am I right? So when you go down the group, the atomic radius increases. When you go down the group, lithium, sodium, potassium, size of the atom gets bigger, or else the atomic radius gets increases. down the group. Understood this? Because when you draw this diagram, we can easily say, because lithium, the outermost shell is there in the L shell, whereas sodium M shell, whereas potassium is in the nth shell. So if you draw a line from the center of the atom, you will understand the distance between the nucleus increases when you go down the group. Got it? Now let us go to the next one. That is a period. So look at this common periodic table, our modern periodic table. So in this, look at this lithium, beryllium, boron, carbon, nitrogen, oxygen. So the group, this is called period, second period it is. So lithium, when you go across, when you go along the period, the size actually gets reduces. Size shrinks. Why? Size shrinks. Why? We will see that now. Just look at this diagram. See what is the difference between, look at this diagram. You could see, so you could see this is for lithium, this is for lithium. The lithium, the electron is in the L shell, right? Even for the boron, the electron present in L shell. So I'll write the electronic configuration: K shell 2, L shell 1. Whereas for a boron, K shell is 2, L shell is 3, right? So that means there are 3 electrons in the L shell, whereas for the boron, for the lithium case, there is only 1 electron in the L shell, whereas for the boron, it is there 3 electrons. You could see 1, 2, 3. But what is one more extra point? The nucleus has 3 protons. Here we have 3 protons, whereas here we have 5 protons. So that is the main difference between these two atoms. But both the outermost shell electrons, in both the cases, the outermost shell electrons are lies in the L shell, right? But the nuclear charge increases in the case of lithium and boron. Lithium and boron. So when the nuclear charge increases, the attraction power also increases. Remember. So 3 plus less strongly attracts the outermost electron than the 5 plus of boron. Remember. So lithium has a less attraction power of these last shell electron. So the distance slightly smaller, slightly larger when compared to boron. Because boron has a 5 plus in the nucleus, it will strongly attract the outermost electron. So the electron come closer towards nucleus. So the atomic size gets reduces. So that's the reason I could draw a diagram like this for boron. What about carbon? Boron is next element is carbon. So in this it has a 6 plus. So further the size gets reduces. So what I'm trying to say is, in this periodic table, what I want to show you is this. When you go across the period, the 1 proton increases in the nucleus and 1 electron increases in the last shell of an atom. That means the size of large scale cell gets decreases because the number of proton present in the nucleus strongly attracts. So 1 proton exists means that will have a strong attraction force on the outer electrons. So that's what main reason when you go along the period, the size gets decreases. Size gets decreases. Lithium size is bigger than beryllium. Boron, the size is smaller than the lithium and beryllium. Lithium size is bigger, beryllium size is smaller, boron is further smaller, carbon further smaller, nitrogen further smaller, like that. So when you go across the period, the size gets decreases because the extra new proton added plays a major role. I hope this will be a very important topic, my dear children. Understand it deeply so that you will get the idea